You're welcome back to physics class, where today we are going to be reviewing Newton's law, and I expect that we are going to have a very interesting time together. We understand that Newton was one of the earliest scientists to have worked on motion, and he was able to give us, among every other law, he was able to give us three laws: the Newton's first law, the Newton's second, and the Newton's third law, governing the behavior of moving objects. And our understanding of the Newton's first, second, third law of motion will properly ground our understanding of the concept of the motion of an object. So we are going to try to review the first, the second, and the third law of motion. First, we are going to go straight into it. The first law of motion, Newton's first law of motion. Newton's first law of motion states that an object will continue in a state of rest or move with uniform motion in a straight line except acted upon by an external force. An object will continue in a state of rest or move with uniform motion in a straight line unless acted upon by an external force. That law is trying to tell us what will happen if no force is exerted on an object. And what Newton is trying to tell us is, if no force is exerted on an object, there are two different things that can happen. Number one, the object will either continue to be in a state of rest. That means in a state where it is not moving at all. An object will continue in a state of rest. If you place an object on the ground, it will remain on the ground for as long as there is no force that is exerted on it. It could take years, it could even take centuries. Once a force is not acted on an object, you don't expect the object to move at all. That's the first situation. Number two, the object will also either move with uniform motion. Uniform motion is what we have described under motion as uniform velocity. An object will either be at rest or be in uniform motion in a straight line unless acted upon by an external force. So we'll say that if there is no force that is exerted on an object, if it is at rest, it will forever be at rest. If it is moving with uniform motion in a straight line, it will continue to move with uniform motion in a straight line. That means if you kick a ball and the ball suddenly achieves a situation where it starts to move with constant velocity, it means that it will always move with that constant velocity forever. Of course, that might be a little bit difficult to take. Yes, no ball will continue to move if played, even if it has been moving with uniform velocity. That is not because Newton's law is not correct. It is because there is now an external force that is going to act on it and bring it to a stop. That is the friction between it and the surface of the floor or the ground or the grass upon which it has been played. Let us remove that friction completely and decide to play that same ball on a perfectly smooth surface where there is no friction, such that we are so sure that once the body starts to move, there is no friction or any other force that is acting on it. The object or the ball will forever continue to move. So Newton is telling us what will happen if no force is exerted on an object. If the object is at rest, it will forever be at rest. If the object is moving with uniform motion or uniform velocity, it will forever move with uniform motion. So the only thing that will not make it continue with these two is if the object is acted upon by an external force. So an object will continue to move, will continue to be in a state of rest or move with uniform motion on a straight line unless acted upon by an external force. That is, there's a part of that law that describes what we call inertia. Inertia is the tendency of an object to continue to move, to continue to be at rest or move with uniform motion in a straight line. If an object is at rest, all objects at rest will naturally always want to be at rest. That is why most of the time you can be a little bit reluctant at waking up very early in the morning. Not because you are not awake, but because to get your body up from bed, it requires a little bit of effort that you are not ready to exert at that time because of your inertia. Inertial is what will always make you remain at rest if you are at rest. And if you are moving with uniform motion, inertial is that part of you that will always want you to continue to move with that uniform motion, preferring not to change it. When an object is at rest, it naturally always wants to be at rest, except there's a push that is exerted on that object. when an object is moving with uniform motion, it prefers to continue to just be like that unless acted upon by an external force or there's a push that is tending to move the object away from that. So the tendency of a body, the reluctance to change your line of motion, the tendency of an object to continue to be at rest or move with uniform motion in a straight line is what is called the inertial of a body. And the inertial of a body is a function of the mass of that object. The larger the mass of that object, the higher the inertia. That is why it is always so easy for heavy objects. It is always very difficult for heavy objects to change their line of preferred motion. Where you need flexibility, mass becomes a disadvantage, because when you want a person to be flexible, you are trying to want the person to adapt to new changes. In that case, the mass of the person, particularly if it has to do with motion, becomes a very, very, very big disadvantage, because the larger the mass, the higher the inertia. And inertia is the tendency of the object to always want to continue with the line of preferred motion, either to be at rest or move with uniform motion in a straight line. For example, on a football field, positions that require that an object will immediately switch its direction of motion are not those positions that you must put very heavy objects, particularly goalkeeping. You need a goalkeeper that will easily adjust to changing direction of the ball. Such can only be achieved if a person has the right kind of flair. Those positions are not the position that you put very heavy footballers. Goalkeepers are known to be lighter, so that they have lower mass and they have lower inertia, and they can always change their position of rest or change their position of uniform motion in a straight line. When they are heavier, if they have already picked a position of rest, they will always want to continue with that position. If they are heavier, when they have already picked a position of uniform motion in a straight line, they will always want to move with position of a straight line. So basically, the Newton's first law of motion states that an object will continue in a state of rest or move with uniform motion in a straight line unless it is acted upon by an external force. The Newton's first law is also called the law of inertia. We can now from there move to the second law. The second law is a more general form that includes the first law. The first law is telling us what will happen if there is no external force. If there is no external force on an object, the object will be in a position of rest, or it will move with uniform motion in a straight line. The second law is now telling us what will happen if a force is exerted on that object. If no force is exerted on that object, the object will either not move at all, or if it has to move, it will move with uniform motion in a straight line. But now, if a force is exerted on an object, what are the things that will happen? Number one, the momentum of that object will change. But before we state the law, we need to talk about momentum. The momentum of an object is the mass of the object multiplied by the velocity of that object. The mass of the object multiplied by the velocity of that object. When an object has a mass and it has a speed or velocity, it will definitely have a momentum. And the momentum can be calculated by multiplying the mass by the velocity. We expect the unit of momentum to be kilogram. The unit of velocity is meters per second. If you multiply the two, you have kilogram meters per second, and that is the unit of our momentum. Now, knowing fully well that momentum is mass times velocity, it is also a vector quantity because it takes the direction of its velocity. If its velocity is forward seeking, the momentum too will be in the forward direction. If the velocity is downward, the momentum will also be in the downward direction. Now, when an object is at rest, we expect that its momentum will be zero. When an object is at rest, yes, all objects will have masses, but an object at rest will not have velocity. So whatever the mass is, if you multiply it by the velocity, it becomes zero. There are two quantities like that are zero for objects that are at rest: the momentum and the kinetic energy. An object that is at rest does not have kinetic energy because you require speed before you can have kinetic energy. So when an object is at rest, you don't have momentum. If a force is impacted on an object, what the force will do is it will cause the momentum of that object to change. The momentum of that object will either change from an higher value to a lower value, or from a lower value to an higher value, or from 0 to a non-zero value, or from a non-zero value to 0. There are so many instances of the exertion of a force producing a change in momentum. In fact, anytime a force is exerted on an object, there must be a change in the momentum of that object. The rate at which that momentum will change is directly proportional to the force that you have applied. That means if you have applied a great force on an object, then the momentum will change by a great amount. If you have applied just a small amount of force on an object, then the momentum will change by a very small amount. That leads us to the second law that we are going to state now. The second law states that the rate of change in the momentum of an object is directly proportional to the applied force, and it takes place in the direction of the force. The rate of change of momentum of an object, the rate of change of momentum of an object is directly proportional to the applied force, and it takes place in the direction of that force. I've earlier said that anytime we exert a force on an object, we expect immediately that the momentum of that object will change, and it will change in the direction of the applied force. That means if I have an object that is not moving and I choose to exert a force on it, it will now start to move, starting to move in the direction of the applied force. If you now start to move in the direction of the applied force, and I hope you know that once it starts to move, it's now having a momentum. Before, while it was at rest, its momentum was 0. So now there's a change in the momentum that has been impacted on that object simply because there's a force that is being exerted on that object. So Newton's second law is trying to tell us that the rate of change in the momentum of an object is directly proportional to the force. Let us assume that the object has an initial velocity of u. If it is at rest, it means that u is 0. If it was moving with a particular velocity, it means it will have a u value that is not 0. By the time you exert a force on the object, let us call the force F, it will now have a new velocity because the momentum will change. The momentum will change not because there's a change in mass, but because there's a change in velocity. Change in momentum can either come from its mass or from its velocity, but in this case, it is coming from the velocity. The object will either move slower, faster, or will stop completely. We assume that the mass of that object is m. The mass remains m even after the impact of that force. We expect, therefore, that if it has a mass of m and it was moving with a velocity, an initial velocity of u, we expect that its momentum, initial momentum, will be mass times initial velocity. I had earlier said that the momentum is mass times velocity. The final momentum will be the mass multiplied by the final velocity mv. So the change in the momentum that has taken place because of the application of that force must therefore be mv minus mu. If that is the case, we are saying that the rate of change in momentum, when we include rates in science, we are describing the quantity. With time, we are describing the change in momentum now with time. So what Newton's second law is trying to tell us is that the rate of change in momentum of an object, is directly proportional to the applied force. It is directly proportional to the applied force. And that is the mathematical expression of Newton's second law of motion. If we continue to work with that, we should have, if we decide to change this to equality, we'll put is equal to, and we have a k value, mv minus mu all over t. Experimentally, the k value here has been determined to be 1. If it is 1, we can now say that the force must be equal to mv minus mu all over t. If we continue with the simplification, we should have F is equal to m open bracket v minus u divided by t. If that is the case, we have an equation that can represent the Newton's second law of motion. But we can still simplify it. Upon review, remember that the first equation of motion, we have worked with it, is v is equal to u plus at. At therefore should be v minus u. If at is equal to v minus u, it means that t or a, if I make a the subject of the formula, a will be v minus u divided by what? T. If a is v minus u divided by t, I can easily substitute for that same expression that I've used in this equation. In that case, I can remove v minus u and I'll put a. So this equation, force is equal to mass times acceleration, is one of the most important equations in physics. In fact, the simple equations in physics are the most important equations. We only just need to know how to use them. Anytime, and this equation explains what the Newton first and second law are trying to teach us. This law is telling us that anytime there's a force, there must be an acceleration. Anytime there's a force, there must be an acceleration that will be impacted on that object by the force. That means if the force is 0, the acceleration must also be 0. Acceleration and force are like twin brothers. The two of them must always be involved in all problems. Whenever there is a force, there must be an acceleration, and whenever there's an acceleration, you can be so sure that there's a force that is acting on that object. It is not possible for you to have a force acting on an object, and the acceleration will still be 0. When the force is 0, the acceleration is 0. And there are two instances in physics where the acceleration can be 0. Number 1, when an object is at rest, it's not accelerating. Number 2, when an object is moving with constant velocity, the object is also not accelerating. I hope you know that those are the two situations that we describe in the first law as situations that an object will go through if there is no external force on it. So if there is no external force, it will be in a situation where the acceleration will also be 0. And those are either being at rest or moving with uniform motion in a straight line. I will state the first law to you so that you see that it's just a clear example of this case. The Newton first law states that an object will continue in a state of rest, acceleration is equal to 0, or move with uniform motion in a straight line, acceleration is also equal to 0, unless acted upon by an external force, unless you decide to exert a force on it. Without a force on it, the acceleration remains 0. That means it will either be at rest or move with uniform motion in a straight line. Now, there's another thing I must also tell you about this formula. F is equal to ma. There are times when an object will be acted upon by more than a force. An object will be acted upon by a force. Which of the force do you think will impact an acceleration on that object? It is the resultant force. It is the resultant force, the resultant of those multiple forces that is going to impact an acceleration upon the object. That means if an object is acted upon by 2 forces and you want to find the acceleration, you will not use either of the 2 forces. Instead, you will now have to go and find the resultant. You can now see, I told you while we were talking about scalars and vector, that somehow scalars and vector has found a way to creep into almost all areas of physics. So when you have 2 forces, then you must find the resultant of those forces, and that is what you must use here to calculate the acceleration of the object. A very good example is if I have an object whose mass is 5. I've been given the mass. Let us now assume that the object is acted upon by 7 Newton and 10 Newton. we expect that it will now have an acceleration. But what will be the magnitude of the acceleration, and what force are we going to use to find that acceleration? The force that we are going to use to find the acceleration must be the resultant of 7 and 10. So we must be able to find the resultant of 7 and 10 acting in the same direction. You can refer to our lesson on vector and scalar quantities for you to know how to find the resultant of forces that are inclined to each other at any angle. But here I'm going to add them. 7 plus 10 will give us 17, and that will be the acceleration upon that will be impacted upon 7 plus 10 will be 17, and that will be the resultant force that will be impacted on that object. There is more to what we are doing. There are a whole lot of quantities that are connected and that we have to learn from this Newton's second law specifically. We have talked about momentum. We have talked about anytime there is a force exerted on an object, there will be a momentum change on the object. If we take the equation that we have used to derive our F is equal to ma, that equation of force is equal to the rate of change in momentum. If we take that equation, we should have, if we break the bracket here, we have mv minus mu all over t. If that is the case, then we can now say, if we decide to cross multiply, that will be ft is equal to mv minus mu. Of course, the name of the quantity that I have here has not changed. It is still the change in momentum. But the quantity that I have on this other side is force times time. Force times time, I'm going to introduce to you now as a quantity in physics that is called impulse. Impulse is the force exerted on an object multiplied by the time that it took you to exert that force on an object. The impulse, therefore, is always calculated as force multiplied by time. Its unit is expected to be the unit of Newton, the unit of force Newton, and the unit of time seconds. So the unit of impulse is expected to be Newton seconds. So impulse, don't forget, is the change in momentum. The two of them are equal. Impulse on one side gives us change in momentum on the other side. So that is why if they want you to find impulse, you are expecting them to give you the force and time. And force and time are not given. You can get it from the change in momentum. Please note that impulse is not momentum. Impulse is the change in momentum. It means when you exert an impulse on an object, there must be a change in the momentum of that object, just like for forces too. And the change that occurs to the momentum is the impulse, not the initial momentum, mu, not the final momentum, mv. It is the change that is the impulse. There are times too they want us to find the change in momentum, and they will not give us mv or mu. They will give us the impulse. Impulse is the change in momentum. Always note that. Now, if I'm using F and T, now, if I have an object, generally, that object has an initial velocity with which it has been moving. Let me call that initial velocity u. If it is at rest, it has an initial velocity too, only that the initial velocity is 0. Now, if suddenly somebody comes and hits the object, hit the object means you are exerting a force on the object. That force is represented in our equation as F. If you hit an object, you are hitting it within an instant of time, though it's a very short period. There's a short period of time through which that force was transmitted from your hand to that object. That is the time that we are using to multiply the force to get the impulse. If I kick a ball, the time that I'm going to use here is not the time through which the ball will travel. It is the short period of time between the time that my leg was in contact with the ball. It's a short period of time while my leg was in contact with the ball. That is the time I'm going to use here. If two objects collide and we want to find the impulse in that kind of a situation, The time is just a short period while the two of them were bound together just before separating or moving ahead after their original line of motion. So please, this time is one that students always mix up with the time for a particular degree of motion that is not even involved here. The time is a short period of time where that impact, where the application of the force is known. We are going to take some example on this aspect so that you start to see what we refer to as impulse as being completely different from so many other quantities that we have learned before. Now, I'll take the first question. A body of mass 3 kg initially at rest. A body of mass 3 kg initially at rest is subjected to two mutually perpendicular forces of 9 Newton and 12 Newton. The acceleration of the body is equal to what? Dash is the acceleration of the body. We're told that we have an object. The object has a mass of 3 kg. It is initially at rest and it is subjected to two mutually perpendicular forces, 9 Newton and 12 Newton. Mutually perpendicular means two forces that are making 90 degrees with each other. So it means one is 9, one is 12. Since the directions are not exactly specified, we can draw them anyhow. We must just draw them in a way that will show that the two of them are making 90 degrees with each other. So 9 Newton and 12 Newton are the force exerted on that object. We now want to find the acceleration. Of course, if there is a force or there are forces, we expect that there will be an acceleration. From this formula, F is equal to ma. The only problem that we have with this case is that we don't know which force to use. Are we using 9 or are we using 12? I said it earlier that we are not going to use either forces if you have more than a force on the object. Instead, you are going to use the resultant of the two. How do we find the resultant of two forces that are acting at 90 degrees to each other? We get their Pythagorean hypotenuse. So we have h squared is equal to 9 squared plus 12 squared. So we have h squared is equal to 81 plus 144. We have h squared is equal to 225. H must be square root of 225, and that should clearly be 15 Newton. So if I know the force that is necessary for the acceleration to be 15 Newton, I expect the mass of that object to be 3 kg. Then I can easily do my F is equal to ma to now find the acceleration that will be impacted on that object. The acceleration must be equal to F all over m. If the F is 15 Newton, the mass will be 3 kg. If I divide them, I should have 5 meters per second squared. And that is the acceleration that will be impacted on this object. Before we move on, we are going to try to also talk about things that we can use to determine the momentum of colliding objects or the application of momentum. Now, we will try to look for concepts that will help us understand the application of momentum. First, we are going to look at what happens when two objects collide and impact a force or momentum on each other. To solve those type of problems, we are going to have to state the principle of conservation of linear momentum. The principle of conservation of linear momentum states that in a closed system, the total momentum is conserved. The total linear momentum is conserved. That's a short way to state it, and it's also correct. If you also want me to expand on that, I will say that the total momentum, when two or more objects collide, the total momentum before collision must be equal to the total momentum after collision. When two or more objects collide, the total momentum before collision must be equal to the total momentum after collision, provided the system is closed or isolated, provided there are no application of external forces. That means if I have an object, let me call that object X, and I have another object Y. If the two collide, the momentum that they will have at the point of collision, if we add it together, must be the same momentum that they will have after the point of collision. It means that if at the point of collision, the mass of X is mx, the mass of Y is my, the initial velocity, the velocity before collision, I will use it as the initial, and the velocity after collision, I will use it as uy for Y. This is happening before collision. After collision, I expect them to now have new velocities. So if this is my X, this is my Y, I expect its mass to be the same as it was, only that this time its final velocity is expected to have changed. Let's call its final velocity, which is its velocity after collision, Vx, and for Y, the velocity after collision to be Vy. What we are saying in essence is, if we can add their momentum before collision, it must be equal to their momentum after collision. Why? Because we said under this law that in a system of colliding objects, the total momentum is conserved. In a system of colliding objects, anytime you have colliding objects, the total momentum must be conserved. That means they must not change. So it means that if I can get the momentum of X, mx, ux, and I can get the momentum of Y, my, uy, if I add them together, it forms the total momentum before collision. If that must also be, I'll get the momentum of S after the collision and the momentum of Y after the collision. When I add them together, what I will have now as their momentum after collision must be equal to what I had before as their momentum, total momentum before collision. Momentum is always conserved anytime objects collide. Anytime objects collide, the momentum is always conserved. But we have to be very careful when applying this equation. Momentum is a vector quantity, I've said before, and the direction of the momentum is also the direction of the velocity. It's also the direction of the velocity. When you are solving this question, you must be very sure about the velocity, the direction through which each of those objects is moving before collision or even after collision. If, for example, we are told that X and Y are in opposite direction before collision, and after collision, they now move off in the same direction. Let's say in the original direction of X. The original direction of X is to the right. After colliding with Y, let us assume that the two of them are now moving in the same direction. I need you to understand that there are two different directions in this question. Initially, X was moving to the right and Y was moving to the left. After collision, the two of them started moving to the right. The velocity, since velocity is a vector quantity and it accounts for the direction in which an object is moving, the velocity of X will not have the same sign as the velocity of Y. It's not possible. I must assume in a question, whenever I have things like this, that there will be a direction I will use for my positive, and there must be a direction I will use for my negative. And all velocity in my preferred positive direction must be positive. All velocities and momentum by extension in my direction in the direction that I've called negative must also be negative. What I mean by that is, if I have a question like this, I can decide that predominantly, since most of the direction I have is positive, so whatever goes to the right is my positive, whatever comes to the left is my negative. If that is the case, it means my ux will be positive because it's in the direction of my positive. My uy will be negative because it is in the direction of my negative. Both my vx and vy will be positive because both of them are in the direction of my positive. So that must be accounted for while I am writing this. So this will not just be uy, this will definitely be minus uy. And this sign will definitely affect this sign. Yes, I am finding the sum, but there are negative sum too that I must be ready to do. So we'll move on. There can be instances too when the two objects will be said to be in the same direction. If they are in the same direction, of course, that should not give me any problem. And we will now be told that the two of them coalesce after collision. Coalesce after collision. Coalesce means they join together after collision. After collision, they join together. If they join together after collision, it means they will now have the same velocity after collision. There is no need for me to put Vx and Vy. Since they are joined together, two objects once joined together must move with the same velocity. It's not possible for them to be together and not travel with the same velocity and travel with the same and with the different velocity. If they are together, they must have the same velocity. So if they are going to have the same velocity in that direction, it means I can call this Vx and I can call this Vy. So I am just looking for a single V in that problem. I'm just looking for a single V in that problem. So two objects can be moving in the same direction and still collide. I hope you know that is very possible. The only condition is the faster one must be at the back. If you are given the speed of these objects and you want to draw them out, if one is having a speed of 4 and the other is having a speed or velocity of 6, definitely for them to be moving in the same direction and still collide, it means the one at the back has to be moving with 6 and the one in front has to be moving with 4. It is not possible that the slower one will be at the back and they'll be moving in the same direction and will still collide. Not possible. So even in our interpretation of the question, we must be so sure that we understand what is it that the question wants us to do. And that is what we are trying to do here. So there are so many instances that you can be given. Please watch out for the direction where you are told that the objects are moving in opposite direction, facing each other before collision. One must be positive and the other must be negative. Please always take that into account. We're going to try to see a question before we move ahead. A trolley A of mass 2 kg traveling at 5 meters per second collides with a stationary trolley B of mass 3 kg. After the collision, the two travel on together at 2 meters per second. What is the momentum of A before collision? What is the momentum of A after collision? Account for the change in the momentum of A. What is the kinetic energy of A before the collision? What is the kinetic energy of each trolley after the collision? During the collision, the kinetic energy gained by B is less than the kinetic energy lost by A. How much kinetic energy is unaccounted for and what has become of it? We are told that there's a trolley. That trolley is called trolley A. It was moving with a velocity of 5 meters per second. Its mass is 2 kilograms. It collides with a stationary trolley B of mass 3. It collides with a stationary body B of mass 3. The mass of this other trolley is 3 kilograms. Because it is stationary, the velocity will be 0. After the collision, the two travel on together at 2 meters per second. This was before collision. After the collision, the two of them now travel on with a velocity The two of them travel on with a velocity of 2 meters per second. This is our body A, trolley B, trolley A and trolley B now traveling together after the collision. The first question, very simple set of questions. There's just a specific reason that I've chosen to take this question. What is the momentum of A before collision? The momentum of A before the collision is the mass of A, 2, times the velocity of A before collision, and that is 10 kg meters per second. I've solved the first one. It's as simple as that. What is the momentum of A after collision? After collision, the momentum of A after collision will be mass of A, this time times the final velocity of A. Final is the mass after collision. The mass of A is still the same, 2 kilograms, multiplied by the final velocity. Both A and B have velocity of 2 after collision. If we multiply that, we should have 4 kilogram meters per second. We can now continue. We are also asked to account for the change in the momentum of A. Why did the momentum of A, why did it change? Initially, the momentum of A was 10. Now, the momentum of B is 4. Where did the remaining 6 go? I think that the remaining 6 must have been given to B. It must have been given to B. How are we going to know that? Let us do the same thing that we have done for A. Let's do it for B. Initially, B has a momentum of 3 mass times initial velocity is 0. B's momentum initially is 0 kg per meter cube, 0 kg meters per second, sorry. The final momentum of B after the collision will now be the mass of B, which is 3, multiplied by the final velocity of B, which is 2. The answer is 6 kilogram meters per second. So when we check very well, we will see that the initial momentum, if we add it together, is 10. The final momentum, if we add them together, is also 10. So the momentum that we ended with, 10, is the same momentum that we started with. So there's a conservation of momentum. So the only thing that happened is why A lost his momentum, lost 6 of his momentum, B gained that exact 6. So the loss of A became the gain of B. In a way, the momentum is conserved. It can be transformed from one body to another, but it will remain, the total momentum that it started with must remain the same. It must be the same momentum that you are going to end with. We now continue. What is the kinetic energy of A before the collision? We want to find the kinetic energy of A before collision. Note that kinetic energy is half mv squared. In this case, I will use U because the initial velocity is what we have before. So that will be half multiplied by the mass before is 2. The velocity before is 5. I'm going to square that. 2 cancel out 2. The answer is 25 joules. A had a kinetic energy of 25 joules before the collision. What is the kinetic energy of each trolley after the collision? I want to find the kinetic energy of each trolley. Kinetic energy of A, the kinetic energy of B after the collision. If in finding the kinetic energy of A after collision, I'm going to use half mv squared. That will be half times the mass of A after collision is the same as the mass before collision, 2. But the velocity after collision is now 2 squared. 2 cancel out 2. This should be 4 joules that is now having. For B, I want to find this kinetic energy, half mv squared for B. This is for A. The final kinetic energy of A. The final kinetic energy of B is half mv squared. That will be half multiplied by the mass of B is 3. The final velocity of B, since it has been moving with the same velocity as A, I will have 3 times 412 divided by 2 is 6 joules. So after collision, the final kinetic energy is 10 joules in total. That of A is 4, that of B after collision is 6, it is 10. Of course, I don't need to find the kinetic energy of B before the collision. It is having a kinetic energy of 0. That is why they did not even ask us to find it, because it was not moving. It was stationary before collision. It was after collision that it started moving. We're now told that what is the kinetic energy of each trolley after I've done that? During the collision, the kinetic energy gained by B is less than the kinetic energy lost by A. Let's check the kinetic energy lost by A. A's kinetic energy before, 25 joules. A's kinetic energy after, 4 joules. So A's kinetic energy reduced by 25 minus 4, which is 21. But the kinetic energy gained by B, B's kinetic energy before is 0 joules. The kinetic energy of B after is 6 joules. So B was able to gain 6, while A was able to lose 21. It is not like in momentum. In momentum, A lost 6, while B gained that 6. But here, A lost 21 joules of his kinetic energy, and B gained 6 joules of his kinetic energy. The question now is, how much kinetic energy is unaccounted for? We have not been able to account for. We have lost 21 joules of kinetic energy, and we have only gained 6 out of it. We have not been able to account for 15 joules of kinetic energy. So we are told what become of it. It has been lost, and most of the time it will be used to produce other forms of energy, like sound. When two things hit each other and you hear the sound, it is most likely the part of the kinetic energy that they had before is what has been converted to sound, and sometimes we have heat. Now, the reason why I've brought up this example is to show you that while anytime two objects collide, their momentum must always be conserved. But that is not true of their kinetic energy. Kinetic energy is not always conserved anytime two objects collide. Kinetic energy is not always conserved. In fact, we are going to see 2 types of collision now. We have as types of collision a special type of collision that is called elastic collision, and another type of collision that is called inelastic collision. Collision becomes elastic if the kinetic energy is conserved. In elastic collision, the kinetic energy is always conserved. In inelastic collision, the kinetic energy is not conserved. In fact, kinetic energy is lost or it reduces after collision. When the kinetic energy of colliding objects reduces after collision, then it is an inelastic collision. But when the kinetic energy remains the same after collision, it is elastic. Meanwhile, I must tell you something about momentum. Momentum is always conserved anytime we have collision. Momentum is always conserved for collision. Whether the collision is elastic or it is inelastic, it is always conserved. The only thing that can help you differentiate between elastic and inelastic is kinetic energy. For elastic, kinetic energy is conserved, but for inelastic, the kinetic energy reduces after the collision. So we can say that in elastic collision, both momentum and kinetic energy are conserved. In inelastic collision, only momentum is conserved, kinetic energy is lost, or kinetic energy is not conserved. And if it is not conserved, it always changes by reduction. The kinetic energy will never increase after collision. It is usually the same after collision if it is elastic, or it will reduce if it is inelastic after collision. So we can see that the example that I have taken on the board here, if I ask you, is it elastic or inelastic? It is inelastic collision, because kinetic energy, 15 joules of kinetic energy I have not been able to account for. So anytime you have collisions that the kinetic energy before is more than the kinetic energy after, it is, and the collision is an inelastic collision, I can continue from there. We can take more examples. Here we are told that a ball of mass 100 grams falls from a height of 3 meters onto a horizontal surface and rebounds to a height of 2 meters. Calculate the change in momentum and B, the change in kinetic energy of the ball when it strikes the surface. There's a surface, an horizontal platform. We have a ball whose mass is 100 grams. It fell from 3 meters and then upon impact with the ground, it rebounds to a height of 2 meters. What we are asked to do is to find the change in the momentum and the kinetic energy when it strikes the ground. When it strikes the ground, what is the change in the kinetic energy and what is the change in the momentum? So I must tell you what I need. What I need now is, number one, what's the velocity with which it hits the ground? I'm going to call that one the velocity before impact with the ground. And with what velocity will it leave the ground after impact? When you want to find the change in momentum, you need the velocity just before the impact and the velocity just after impact. Even for collision problem, you need the velocity just before collision and the velocity just after collision. So to do that, I must find the velocity with which this object hits the ground. That will be the velocity before. I must find the velocity with which it left the ground. That will be the velocity after the collision. There are essentially 3 things taking place in the motion of this object, but I need only one out of it. The object is falling, that's number one. The object is contacting the ground. The ground is impacting its force on the object, or the object is impacting itself on the ground. That's number 2. And number 3, it rebounds. I only need the part where it's impacted with the ground. That's all. It is just that I cannot solve that part independently because one part led to the second part, and the second part gave me the third part, which is the rebounding part. So, particularly to get this velocity, I will now have to work with motion, and we are going to see what we are going to do. This question has given us the acceleration due to gravity to be 10. Acceleration due to gravity to be 10. The acceleration due to gravity, G, is 10. So I'm going to do a bit of motion in this question. How will I do that? I need to know the final velocity with which this object touches the ground. I told you earlier on under motion that anytime an object is falling, it will fall from rest. It will have an acceleration of 10. That's acceleration due to gravity because it's falling in the direction of the acceleration due to gravity. I will use these 3 as the distance through which it fell, and I'll be able to find the final velocity, which will give me, it is the final velocity for the falling motion, but I will take it as the initial velocity for the impact. The velocity with which it's going to strike the ground is the velocity it will also have just at the point of impact, just before impact. So I can find that. I know U, I know A, I know 3. I know S to be 3. I want to find V. I can do V squared is equal to U squared plus 2AS. I can now use V squared is equal to U squared is 0 squared plus 2 multiplied by A is 10 and S is 3. So I will have V squared is equal to 60. V itself will be square root of 60. And square root of 60 I can obtain as 7.75, 7.75, 7.75 meters per second. Number 2, I will analyze, okay, before we go there, what I have just calculated is the velocity with which this object will strike the ground. That is what I will use as my velocity before impact, 7.75 meters. You might be a little bit confused about the fact that why do I have to represent it with V here and I'm calling it U here? That is simply because I told you that there are 3 different types of motion taking place here. Number 1, the falling object. That V is the final for the falling part. Number 2, the impact. That the final for the falling will be the initial for the impact. So I'm using it as the initial for the impact. The final for the impact, that means the final velocity after impact, will be the initial for the rising. So what I will do now is, similarly, I'm going to find the initial velocity for the rising part of the motion. I'm going to find the initial velocity for the rising part of the motion. What are the things that I already know? I know the final velocity. Anytime an object goes up, it must continue to go up until its final velocity is 0. I know its distance to be 2, and I know the acceleration to be -10 because it is now moving against gravity. So I can also use my v squared is equal to u squared plus 2as. I can use my v squared. My v squared in this case is 0 squared is equal to u squared is u. Now we can continue to find the velocity just after impact as the velocity with initial velocity of the rebounds. That will be v squared is equal to u squared plus v in this case is 0. U squared plus 2 times a is -10 multiplied by s, which is 2. We have 0 is equal to u squared minus 40. That means u squared must be equal to 40, and that means u must be equal to square root of 40. And square root of 40 is 6.32. That is the velocity with which this object took off for the rebounds. Of course, that has to be the final velocity after impact. That should be the final velocity after, because it was after impact that it now took off. So if it took off with a velocity of 6.32, it means the final velocity after impact is 6.32 meters per second. So we can now get the change in momentum, because that is what the question wants us to find. The change in momentum of the object after impact with the ground. How can we do that? The formula for change in momentum is mv minus u. There's something I want you to check again in the problem. The object reverses its motion after impact. It came down, and after impact it went up. So the velocities are not in the same direction. I will have to take one positive. I'm going to take this one as positive. I'm going to take this one as negative. If you do the reverse, take this as positive and this as negative, you will still get the same answer. One other thing I have to do before completing the change in momentum is the mass. I've been given the mass of the object to be 100 grams. That means I must change it to kilogram by dividing by 1,000. That mass must be 0.1 kilogram. So the change in momentum will now be 0.1 multiplied by the final velocity 6.32 minus the initial velocity is minus 7.75. If I do that, that should be 0.1 open bracket 6.32 plus 7.75, and I can continue with that. This is 1.407 kilogram meters per second. That is our change in momentum. We are also asked to find the change in kinetic energy upon impact. How do we find the change in kinetic energy? The change in kinetic energy of that object must be the final kinetic energy minus the initial kinetic energy. So the final kinetic energy will be half mv squared. The initial kinetic energy will be half mu squared. I'm using u for the initial velocity before impact, and we can easily put that in. That is half times the mass is 0.1. The final velocity after impact is 6.32 squared minus half is 0.1 multiplied by the initial velocity before impact is 7.75. You ask me now that I'm not using my negative because speed is what we use to get kinetic energy, not velocity. And speed does not require the signs, does not have direction. Even if you put the negative, you will still be correct, because by the time you find the square of a negative velocity, you will definitely have positive. So we can bring out our calculator to solve all of this. The kinetic energy before should be 1 over 2 multiplied by 0.1 multiplied by 6.3 squared, which is 40, 0.5 multiplied by 0.1 times 40. The answer is 2. We do the same for the value after. The value after should be 0.5 times 0.1 times 60. The answer is 3. That should be minus 1 joules. The reason why we have a negative is because the initial kinetic energy is actually greater than the final kinetic energy. So there's a change of 1 because the kinetic energy has reduced after the impact. So I should have done the initial kinetic energy minus the final. Can be still correct if you understand negative as a loss. The object has actually lost kinetic energy, and that is why upon rebounds, it was not able to get to the same level that it was thrown. This impact, for example, is not an elastic impact. It is definitely not an elastic impact. If it were to be elastic, the object will come down from 3 and it will get back to 3. That way, we will say that the kinetic energy that it has before impact is the same kinetic energy that it has after impact. But it has a kinetic energy that made it fall from 3 before impact, and the kinetic energy with which it left did not make it get to 3. So that is why we have a deficit in the kinetic energy that we have just calculated. So we now move on to Newton's third law. Newton's third law states that action and reaction are equal and opposite. Another way of saying that is, to every action there's an equal and opposite reaction. To every action there's an equal and opposite reaction. And there are so many instances in physics where we can be using the Newton's third law and the Newton's second law. Anytime a force is exerted on an object, that object is going to exert another force in the reverse. It is necessary for us to understand that if you kick a ball, it is because you have exerted a force on the ball. Technically, we expect that the ball will also exert a force on you. That is why if you are not wearing a leather ball and you decide to kick a leather ball, you are not wearing a leather boot, and you decide to kick a leather ball as hard as you can, you will feel a pain in your leg. That pain is due to the reaction of the ball on your leg, because you have exerted an action force on the ball, so the ball will reciprocate by exerting a reaction on you. If you slap a person as hard as possible, you are also going to feel the pain on your palm. Why? Because while your slap is an action, the person's face will also exert a reaction on you. If you box, if you hit a wall, yes, you have exerted a force on the wall. That's even a very appropriate illustration. If you exert a force on the wall, you will have to hold your hand because the wall will also exert a reaction on you. To every action, there's an equal and opposite reaction that you are also going to experience. And there are so many instances where we can begin to see this one. We are going to check application of Newton's third law in recoil of a gun. We are going to see man in a lift, and we are going to see motion of connected objects. Initially, I must tell you, when you stand on a weighing machine, the weighing machine is expected to record your weight. It is expected to record your weight. But technically, it is not recording your weight. If you hold a spring balance, if you stand by holding a spring balance, you expect the spring balance to record your weight, but technically it's not recording your weight. Even we used to say it under the very first topic in physics, units, measurements, and quantities. Measurement, quantities, and units, that the spring balance measures weight. Yes, it is acceptable, but in technical terms, there's nothing that can measure weight because your weight is a field force. It's a force field. It's a force that comes from the field of the earth. You cannot measure it. And I'm going to give you some examples to show that you cannot actually measure weight. When you stand on a weighing machine, you get your weight because the machine is recording a force that is equal to your weight at that time. The machine is recording a force that is equal to your weight. So you just assume that it is giving you your weight. When you hold a spring balance, the spring balance is recording a force that is equal to your weight. It's recording a force that is equal to your weight. For example, anytime you stand on a surface, we mentioned it under friction, that there is a downward force on the surface from you. That thing is called your weight. But the surface is also holding you back up with a normal reaction R. The surface is also holding you back up with a normal reaction R. Now, if there's no movement, your R and your W are equal. Your R, your reaction, and your W are equal. This is the contact force that the weighing machine is recording. But because it is equal to your weight, it takes a value that makes you understand your weight. The same thing when you are holding a spring balance. Your weight is acting vertically downward, but there's a force that you are using to hold the spring balance, or that the spring balance is using to support you so that you don't fall. Now, what if there's no motion in this system? The force, that tension along the string connected to the spring balance from you, is equal to your weight. And because it is equal to your weight, the spring balance will measure the tension, and that tension, because it is equal to your weight, will make you understand what your weight is. So nothing records weight in essence. What they actually record are other forces. It is only a contact force that can be measured by instruments. And tension, normal reaction are contact forces. You need to be on the surface before normal reaction can be exerted on you. You need to be holding a string before a tension can be acted upon you. Now, nothing records weight. What we have is it records the tension and it records the normal reaction, or some other forces that are also equal to your weight. That means if there are situations in which I can get the normal reaction to be different or unequal to the weight, the weighing machine will record a value that is not your weight. The same thing here. If something happens that makes the tension to be different from the value that your weight will be, the spring balance will record that tension, and that is not your weight. One of such takes place for an object that is held up inside a lift. When you stand on a lift, let us assume that you are standing on a weighing machine in a lift. You will have a weight which is downward, but the weighing machine or the lift will exert a directly opposite normal reaction force on you. If the lift is not moving, R is equal to W, so the weighing machine will give you an idea of your weight. But let us look at a situation in which the weighing machine is moving down with an acceleration. We are going to look at that, case 1. Let us also look at a situation in which the weighing machine you are standing. Let's even try to change the rhythm of the question. You are holding on to a spring that is attached to a scale, to a spring balance. For this time, this system is moving up with an acceleration. It's moving up with an acceleration. It's the same thing. Here we have a weight, but what has come to replace the weight here is the tension between you and the machine and the spring balance. Then we'll look at the third case in which the object is moving. Yes, you are standing on a weighing machine, but the object is moving up or even down with an acceleration that is equal to 0. How is that possible when the object is moving with constant velocity? Then the acceleration is 0. We are going to look at this situation too. Again, we have your weight and we have a normal reaction exerted on you. And lastly, let us also consider a situation in which you are holding a spring balance and the object is now, the lift is now falling with an acceleration that is equal to acceleration due to gravity. It's falling with an acceleration that is equal to acceleration due to gravity. Remember that the two forces here will be your weight and your tension. Your tension and normal reaction are the supporting force in all of them. So how do you think the weighing machine will fare in each of these cases? What do you think the weighing machine will record, and how is that related to the weight of the object? I want to use this to show you an example of how it is possible for a weighing machine or a spring balance not to always record your weight. Now, we can use our equation of F is equal to ma, because I said anytime there's an acceleration, there's a force that is producing that acceleration. There are two forces here, your weight and your normal reaction. Those are the two forces on you. Because you are moving downward with an acceleration, and I said that the force we are going to use here is neither of the two forces, it's the resultant of the two forces. If you have a force on you, that is the force that is responsible for the acceleration. But if you have more than a force on you, that is the force, you have to find the resultant of the force. That is the force that will be responsible for your acceleration. If this object is going down with an acceleration, I expect that the resultant force, it is because the resultant force is W minus R. If R is greater than W, this system will move up. But because it is moving down, W should be greater than R. The resultant force, therefore, should be W minus R. It is like if you have an object whose force, the downward force on that object is 10, and the upward force on that object is 6 Newton. The force that is responsible for the acceleration is 4 Newton. That is 10 minus 6. So that is exactly what I'm going to do here. So the force that is responsible for the acceleration will be W minus R. And it is equal to MA. If W minus R is equal to MA, I want to find the R, the normal reaction. The normal reaction, if I make it the subject of the formula, will be W minus MA. And I hope that the normal reaction will be equal to, we already know that the weight is always equal to the mass times acceleration due to gravity. It means mg minus ma. So we are going to have a situation where the weighing machine, I just told you it records the normal reaction, will record the normal reaction that is not equal to the weight. In fact, it will record the normal reaction that is less than the weight by a difference of MA. We are going to use a numerical example to solve that so you see what I mean. So in a situation where a lift is falling with an acceleration of A, check the weighing machine if you already know your weight. It is not going to record your weight. It is going to record the value that is less than the weight, and that is because it is not measuring your weight directly, it is measuring the normal reaction. Let us move on here too. Where the object is moving up and there are two forces on it, it is because there's a resultant force upward. T is acting upward, W is acting downward, and the object is now moving up. It means T is greater than W. So I can say that if I have to apply my F is equal to MA, my F in this case must be T minus W. If it is T minus W, I will equate it to MA. What is my T? Let us assume that I don't know it yet. Minus W is mg is equal to MA. That means T must be equal to MA plus mg. And if that is the case, that is what this spring balance will record. It will record your weight. You will find out that it's going to record a value that is more than the weight. And that is because the value of the T has increased by a difference of MA. So anytime a lift is going up, check the weighing balance that you are standing on or the spring that you are holding. It is going to record something that is slightly more than your weight. Where the object is moving with an acceleration of 0, either upward or downward, very simple. What do we do there? We use F is equal to MA. Let us assume that it is going up. If it is going up, technically we can feel like the normal reaction is more than the weight. So there's a resultant force upward. That's why it is moving up. The force in this case will be R minus W is equal to MA. Our R must be equal to W plus MA. But luckily the acceleration here is 0. We'll see that R is equal to W and your R is equal to mg. In a situation where the object is not accelerating, the spring balance or the weighing machine that you are standing on will record a normal reaction value that is exactly equal to your weight. So if your weight is a particular value, check the machine. That is what the machine will also give to you. We can now move on to a situation where the object is falling with an acceleration that is equal to acceleration due to gravity. When an object is falling with an acceleration that is equal to the acceleration due to gravity, in physics we say that it is falling freely. It is not falling under guided motion. If I throw this marker down, it will fall freely because the only force on it is its weight. So we'll look at a situation like this. Let us assume that the object is going down with an acceleration that is equal to the acceleration due to gravity. We will say that F is equal to MA. My F here, as always, will be the resultant of the two forces on it. Because it's going down, we expect W to be larger than T. So that will be W minus T. If it were going up, it will be T minus W, as in the case for others that I've done. If that is the case, W minus T will be my resultant force. It will be equal to MA. This time, the A with which the lift is falling is G. So I will have W minus T is equal to mg. So T therefore must be equal to W minus mg, and T must be equal to W, which is mg, minus mg. T must be equal to 0. Anytime an object is falling freely, falling with an acceleration, check, put a weighing machine under your feet at that time if you are falling freely. If you are falling unguided, you will find out that the weighing machine will not record any value. A very good example, a very good illustration of that is you can put a weighing machine directly under your feet, come out of the corridor of your house. That's a very dangerous experiment. I don't want you to do it. I'm just giving you an instance. Come out of the corridor of your house and throw yourself down. Check while you are falling if there's enough time for you to even check. check what the weighing machine is recording at that time. It is not recording anything. In fact, you can even glue it before fall to your leg to be so sure that it is permanently glued to your leg. It is not recording anything. Yes, you still have your weight, but because it is also falling freely, it does not have the time to support you with any force. There's no tension to hold you. There's no normal reaction to hold you. So it is not exerting any force on you, and it's going to record the value of 0 to show you that weighing machine spring balance actually record the tension and the reaction. Those are the force of support. They do not actually always record the weight. They record the force that we can call the weight, and we'll use them to evaluate the problem as such. We'll move on to other application of Newton's law, the recoil of a gun. I want you to check those very good American thriller movies where you have your snipers shooting the gun. It is a known knowledge that when they shoot the gun, the gun will jack backward at the point that the bullet comes out from it. That is why if it is an heavy-duty gun, you require a person that has a very large mass to hold it. Else, it is even possible that the gun will throw off the person if the person is not does not have the sufficient mass to operate it. The reason for that is when a gun fires a bullet, the bullet moves in a direction. But that is an action. The gun has shot the bullet in a direction. Before the bullet leaves the gun, it's going to exert an opposite reaction on the body of the gun, and that will jack the gun backward. So while the bullet moves in a direction, the gun moves in the opposite direction. And sometimes that velocity with which the gun is going to jack backward can be so high at times. The velocity with which the gun jacks backward after shooting the bullet is called the recoil speed, if it is speed, or the recoil velocity of the gun. We don't use recoil for the bullet. The bullet is having its normal velocity. It is the jacking backward of the gun that we are talking about that we describe as being the recoil. So the recoil velocity of the gun is the backward velocity with which the gun moves after shooting the bullet. And we can find it. Let us assume that mg is the mass of the gun. mb is the mass of the bullet. Let us assume that ug is the initial velocity of the gun. ub is the initial velocity of the bullet. Those are the velocities of the bullet and the gun before the shot. Now vg and vb are the final velocity of the gun and the bullet after shooting. So this is vb after shooting, the velocity with which the bullet will leave. This is vg, the velocity with which the gun will jack backward. If we write the equation, if we use the momentum conservation theory to write an expression for this, we'll say that the total momentum before shooting must be equal to the total momentum of the gun and bullet after shooting. The total momentum after shooting mind you, before shooting, all of the gun and the bullet were at rest in the hand of whoever wants to use them. So there's no momentum before shooting. There's no momentum before shooting because the gun was at rest and the bullet was also at rest initially. Now, after shooting, we expect the gun to have a velocity of Vg and the bullet to have a velocity of Vb. So if you take into account that the two velocities are in opposite direction, then we can decide to call this positive and this negative. Or you call this negative and this positive. So that will be the momentum of the gun after shooting plus the momentum of the bullet after shooting. The shot will now be equal to the momentum of the gun after shooting will be m of the gun, u of the v of the gun. After shooting, the momentum of the bullet will be m of the bullet, v of the bullet. We are going to put a negative here because it is moving in the opposite direction. If we do that, we have 0 is equal to mg vg plus mb vb. And if you bring this to this side, we have mg vg must be equal to mb vb. If that is the case, vg must be equal to mb vb all over mg. And this is the formula for the recoil velocity of the gun. Note that I've already assumed that it is in the opposite direction, so the minus is not reflected in this equation. If I had left it as positive, I would have had minus. That minus suggests that the gun will move in the opposite velocity to the bullet. And that is what we have. We'll get to the point where we are going to use this. Lastly, we are going to talk about the motion of connected bodies. The motion of connected bodies. And when we are done with that, we'll take examples, then we'll round up. We conclude the topic. And an object is placed on a plane. That object, as I've said, we have a weight and it will have a normal reaction on it. If we have a pulley attached to the plane such that another object can be connected to the object on the table. Let us describe this object as object A and this other object as object B, so that another object can be connected to it. Then it is possible that there is a motion, because there are now more than just these two forces. I will try to indicate the other forces. Because B is hanging downward, it will have a weight. This is the weight of B. Let me call this the weight of A. There will be a tension that will act along the rope, trying to pull B up. That tension will also be the tension that will act to move A in the direction of fall of B. So this pulley, what this pulley has done is to help me transmit the tension that is acting through the rope on B to help me transmit it to A, and tension is always shown away from the object. So these are the combination of forces that I have. Now, one other thing that we can also have in this system is the friction. If we are told that this surface is smooth, then there's no friction. This is all about the force that's available. But if there's a friction, because this object is now trying to be pulled to the right, friction will exert itself in the opposite direction. Refer to our class on friction to understand how to get the direction of friction. So that is all of the forces that can be shown on this connected as A and B are connected with a string. So now I can now be asked to find the common acceleration of this system. What's the common acceleration of this system? I will assume a direction in which I'm expecting this object to go. If there's going to be a fall at all, if there's going to be a movement, I expect this B to fall and this A to move in this direction. It is not possible for A to move in this direction and B going up. That is naturally impossible. It cannot even move in the direction of friction. It's not possible. Friction cannot cause motion. So the only possible direction, if there's going to be a movement, is for B to fall and drag A along with it. What I will now do is I will write the equation F is equal to ma for both A and B, describing their motion. One thing I'm so sure that they will now have in common is A, if they have to move, they will move with the same acceleration because they are connected. So now if they are dropping with an acceleration, the acceleration that B is dropping with will also be the acceleration that A will have to slide with on the table. Now I can find my F. Since this object is falling, remember that WB must be greater than T. because this object is moving downward. So the resultant force in this system will be WB minus T is equal to MA. That M is the M of B. For these two, I will write my F is equal to MA. This object is moving horizontally, so the horizontal forces on it will be what I will consider T and the friction if there's a friction. If this object is to move in this direction with an acceleration, it means T is more than the friction. That's why the object is moving in that direction. So I can write my resultant force as T minus the friction is equal to MA. My A in that case is the mass of A. I can now solve the two equations simultaneously for T and A, which is in both equations. We are going to take examples and we'll try to see how all of this can be applied. The first part that we are going to look to is an elevator of mass 1,200 kilograms moves vertically downward with an acceleration of 1. What is the tension in the suspending cable? It's an elevator. It is moving downward, vertically downward with an acceleration of 1. What is the tension in the cable that is suspending it? The cable that is suspending it, which is preventing it from falling. We are not even told that there's anybody inside the elevator. It's the whole of the elevator that we are considering. So we want to find the tension in the suspending cable. Let us show our forces. The elevator will have a weight of its own. And because the cable is used to suspend it, that cable will have a tension. And that is what we are looking for. So we are given the mass of the elevator. The mass of the elevator itself is 1,200 kilograms. So I can now use my F is equal to MA, very important equation. Because it is falling, I expect the downward force to be more than the upward force. So the resultant force will be W minus T, and that is equal to MA. So I can now do T equal to W minus MA, because it is T that they want me to find. My W is mg minus MA. I can factorize my M as G minus A. My M should be equal to 1,200 multiplied by G, which is 10, and A, which is 9. That should be 1,200 multiplied by 9. And 1,200 multiplied by 9 should be 10,800. 10,800 Newton. That is the answer to that question. We now move on to other examples. We are given a system of force. This is said to be 6 kilograms, and this object is said to be 3 kilograms. Two connected objects. I've been told that two blocks of masses 3 kilograms and 6 kilograms are connected by a light inextensible string which passes over a smooth pulley, as shown above. Assuming that the 6 kilogram mass is sitting on a smooth surface, what will the body accelerate with? What will be the acceleration of the body? Very simple. It looks very much like the example that I've done. This we have a weight. We can calculate the weight as a mass times its acceleration due to gravity. That should be 60. 6 times 10. It will have a normal reaction, which is also 60. This will have a weight, which will be 30. And it will also have a tension because there's a string. The tension will be transmitted to the 6 kilogram object used through the pulley. There's no friction on this table, so I won't consider friction at all. So what I will just do, therefore, is to write my equation of F is equal to MA and the equation of F is equal to MA. But before then, I have to assume a direction in which this object will move. It can only move downward, and this will follow in this direction. Because they are connected, they will have the same acceleration. So I can write my F is equal to MA for the 3 kilogram object, and I will also write it for the 6 kilogram object. My F in this case is 30 is the resultant force, and there are two forces on it, 30 and T. Because I assume that it is falling, the force will be 30 minus T is equal to M, the mass is 3, multiplied by A. For this, it is moving in this direction, and the only force in that direction is this tension. So I'll say the tension is equal to, what is the mass? 6 multiplied by A. So I can substitute this for it. I will have 30 minus 6A is equal to 3A. And that will be 30 is equal to 9A. A must be equal to 30 divided by 9. 30 divided by 9 must be equal to 10 all over 3, and the answer should be 3.33 meters per second squared. That's the acceleration. If I've been asked to find the tension, I can just slot in the value here, and I will get my tension. Now, the last question, the last but not the least. I have an object, I have a pulley. This object on an inclined plane is connected through a rope to another object. The first object is 2 kilograms and the next is 3 kilograms. This is 2 kilograms and the next is 3 kilograms. So I can show all of the forces on this object. Here we have to borrow some of what I've already told you while we're doing friction on an inclined plane. We have to use them. We are told that the 2 kilogram mass on a smooth inclined plane, the plane is also smooth, so there's no friction, is connected over a smooth pulley, to a 3 kilogram mass as shown above, What is the acceleration of the system? The acceleration of the system is what I want to find. Mind you, I can find the downward, I can indicate the force. I expect the weight of this object to act down. I also expect this to be the tension. With the pulley, the tension will be transmitted to this 2 kilogram object as T. Now, this will also have its weight, but I won't use that weight. As we have said under friction, please consult, go through our class on friction for you to understand what I said about the weight of an object that is placed on an inclined plane. We are given the angle of inclination, mind you, to be 30 degrees. The weight is 20, that's mass times acceleration due to gravity. The weight here will be 30, that's the mass times acceleration due to gravity. What we always do with weight on an inclined plane is to resolve it. Into two preferred directions. I said if this is 30, this must also be the angle 30. I said if we resolve it into two components, the component beside the angle will be cos. This is 20 cos 30, and this will be 20 sin 30. 20 sin 30, and 20 sin 30 is 10. There will be a last force. That's the normal reaction, which is perpendicular to the plane, but I don't think we are going to get to use it at all. So what we need to do now is to write our equation F is equal to ma for each of these two objects that is present. We'll write F is equal to ma. The force here is going to be the downward minus the upward, because if there is going to be a movement, let me assume that it will move like this. It will move down with an acceleration, and this will move up. It is also possible in this case that the 2 kilogram object slides this way and 3 kilogram goes up. So if that is going to be the case, my acceleration will be negative. You can assume any direction. By the time you solve it, if it is the reverse of the direction you have taken, you will still get the same answer, but you will get a negative answer as your acceleration, and you can easily just reverse it. But I'm assuming that this 3 kilogram must fall and this 2 kilogram must slide in that direction. You must always assume a direction for your acceleration before you can begin to solve motion on connected objects. So if I write my F is equal to ma, the force here is going to be 30 minus T. The mass is going to be 3 kilograms, while the acceleration is A, and that will be 30 minus T is equal to 3A. Here, the object is moving up, so I'm assuming that T, the force in the direction of that acceleration is more than 10. So if I write my F is equal to ma for the 2 kilogram object, it will be t minus 10 is equal to 2a. I can make t the subject of the formula. That would be 2a plus 10. So if that is the case, I can just slot in this value directly into this expression to find my acceleration. That would be 30 minus, instead of t, I will have 2a plus 10 is equal to 3a. That should be 30 minus 2a minus 10 is equal to 3a. 30 minus 10 should be 20. 3a plus 2a should be 5a. A therefore must be equal to 20 divided by 5, and that will be 4 meters per second squared. And that is our final answer for this question. With that, we have come to an exciting lesson on Newton's law of motion. Join us the next class when we'll be reviewing another very important topic in physics. Thank you.